Look closer. Beyond the world we see, beyond the limits of our senses, lies a hidden architecture, a realm not of objects, but of probabilities, not of certainties, but of quantum whispers. This is the nanoscale, a frontier 100,000 times smaller than the width of a human hair, where the familiar laws of physics collapse, and reality itself begins to play by an entirely new and astonishing set of rules. Our journey begins with a descent. We move past the world of the visible, through the intricate tapestry of biological tissue, and into the bustling metropolis of a single cell. Here, proteins, the workhorses of life, fold and unfold in a complex ballet. But we must go deeper still. Down, down we go, until the very concept of a solid surface dissolves into a shimmering haze of possibility. Here, at the scale of 1 to 100 nanometers, Isaac Newton's classical mechanics, the physics of thrown baseballs and orbiting planets, loses its authority. We have entered the domain of the quantum. In this world, matter behaves in ways that defy intuition. Consider gold. In our world, it is a familiar, inert, yellow metal, but when sculpted into particles just a few nanometers wide, it transforms. It glows with a vibrant, ruby-red light. This isn't alchemy, it's physics. The gold nanoparticles are so small that their electrons begin to resonate with light in a collective oscillation, a phenomenon known as plasmon resonance, absorbing green light and radiating red. They become something new, something potent. Or witness the magic of quantum dots. These are semiconductor nanocrystals, tiny islands of matter so small they function as artificial atoms. Their secret lies in a quantum effect called confinement. By precisely controlling their size, we can dictate the exact color of light they emit when energized. A larger dot glows red, a slightly smaller one green, smaller still, a brilliant blue. Each one a perfect tunable beacon, thousands of times brighter and more stable than conventional dyes. This is the power of nanotechnology, the ability to engineer matter at its most fundamental level, to compose a new reality, atom by atom. And this power is already being harnessed to fight our most formidable diseases. We are now inside the human bloodstream, a turbulent river of life, carrying oxygen and nutrients to trillions of cells. But for many, this river also carries a deadly cargo, the seeds of cancer. For decades, our primary weapon has been chemotherapy, a sledgehammer approach that poisons the body to kill the tumor, inflicting devastating collateral damage on healthy tissue. But nanotechnology offers a new strategy. A Trojan horse. Meet the nanomedical vanguard. This is a liposome, a microscopic sphere of fat, engineered to carry a payload of cytotoxic drugs. But it has a secret weapon. Its surface is coated in a dense brush of polymer chains called polyethylene glycol, or PEG. This cloak of invisibility allows it to drift past the body's immune system, which would otherwise identify and destroy a foreign invader. It is a ghost in the machine, silently hunting its target. Cancer tumors grow chaotically, creating leaky, disorganized blood vessels. Nanoparticles are the perfect size to slip through these cracks and accumulate within the tumor microenvironment. Furthermore, by engineering their surface with a positive charge, they are drawn to the negatively charged membranes of cancer cells, a process known as receptor-mediated endocytosis. The cancer cell itself is tricked into welcoming its own destroyer. Once inside, the liposome structure breaks down, releasing its lethal cargo directly at the heart of the enemy. The cancer cell is annihilated from within, while the healthy cells, just a few micrometers away, remain untouched. This is not science fiction. This is the dawn of precision medicine, a new era where we fight disease not with poisons, but with intelligence, an intelligence born from our mastery of the nanoscale. But the challenges we face are not confined to our own bodies. They extend to the very edge of the solar system. Space. The final frontier is an environment of breathtaking beauty and unimaginable hostility. Beyond the protective shield of Earth's magnetosphere, astronauts are bombarded by a constant storm of high-energy cosmic radiation. These particles can tear through DNA, increasing the risk of cancer and degenerative disease, representing one of the greatest obstacles to long-duration spaceflight to Mars and beyond. Conventional shielding, like thick plates of aluminum, is far too heavy to be practical for interplanetary missions. The solution, once again, is found in the quantum architecture of matter. This is a boron nitride nanotube, or BNNT. Its structure, a rolled-up sheet of hexagonal boron and nitrogen atoms, is incredibly strong, lightweight, and thermally stable, but its true genius lies in its ability to absorb radiation. The boron atoms are exceptionally effective at capturing neutrons, one of the most damaging forms of secondary radiation. When embedded within spacecraft composites, BNNTs create a shield that is not only lighter, but vastly more effective than traditional materials. The innovation extends to the astronaut's very skin. Future spacesuits will be woven from a fabric of nanomaterials. Carbon nanotubes, 1,000 times stronger than steel at a fraction of the weight, will provide unparalleled protection against micrometeoroids. And interwoven sheets of graphene, the best thermal conductor ever discovered, will efficiently dissipate heat, keeping astronauts cool even during the most strenuous spacewalks. We are building our future in space with materials forged in the quantum realm, creating vessels and suits that are not just built, but engineered for survival. Yet, some of our greatest challenges lie not in the stars, but right here, on our home planet. Our digital world runs on energy. These data centers, the brains of our global civilization, consume titanic amounts of electricity, not just for computation, but to keep themselves from melting. The heat generated by billions of transistors is a thermodynamic crisis in the making. Nanotechnology offers a cooler path forward. By suspending nanoparticles in cooling fluids, we can dramatically increase their thermal conductivity, creating nanofluids that can whisk heat away from processors with unprecedented efficiency. Water security is another looming global threat. Desalination, turning seawater into fresh water, is an energy-intensive process. But membranes made from carbon nanotubes are changing the equation. The incredibly smooth, narrow channels of these tubes allow water molecules to pass through with almost no friction, while rejecting larger salt ions. This nanofiltration could cut the energy cost of desalination by up to 50%, promising a future of water abundance. And what of the carbon dioxide warming our atmosphere? Here, nanotechnology provides perhaps its most elegant solution. Metal organic frameworks, or MOFs, are crystalline super sponges. Their vast internal surface area, a single gram can have the surface area of a football field, makes them perfect for selectively capturing CO2 directly from the air. But we can go further. By integrating metallic nanocatalysts into these frameworks, we can not only capture carbon, but convert it, using it as a raw material to synthesize clean fuels and valuable chemicals. We can turn our greatest liability into our greatest asset. With such power comes profound questions and even fear. In the 1980s, the concept of gray goo, a hypothetical plague of self-replicating nanobots consuming the biosphere, entered the public consciousness. It's a terrifying image, but one that has little to do with the reality of modern nanotechnology. The dream is not to build uncontrollable autonomous swarms. The dream is to build factories. This is molecular manufacturing, not in a petri dish, but inside sterile, tabletop vacuum chambers. Here there are no free-roaming replicators. Instead we see deterministic mechanical assembly lines, robotic arms guided by lasers, position molecules with atomic precision. It is the ultimate form of manufacturing, building complex products from the bottom up, with no waste, no pollution, only perfection. This is not about unleashing chaos, it is about achieving absolute control. From the inner space of our own bodies to the outer reaches of the cosmos, from securing our planet's resources to building the very tools of creation, nanotechnology is not a distant dream. It is a quiet revolution that is already reshaping our world. We are learning to speak the fundamental language of the universe, the language of atoms. And by mastering this atomic language, we are beginning to write our own future, unlocking possibilities as infinite as the quantum realm itself.